Okay, so the Rouché-Capelli theorem gives us a basic taxonomy of systems that are in reduced row echelon form. Remember, the first thing we can quickly verify is whether or not the system is consistent by checking whether or not there's a pivot in the augmented column. If the system's inconsistent, we know there's no solution, so there's nothing to do in terms of solving the system. But if the system is consistent, so if there's no pivot in the augmented column, the question now is, well, how do we actually find the solutions? The Rouché-Capelli theorem tells us that if there are no free variables, so if the nullity of the coefficient matrix is 0, there will be exactly one solution. And if we have free variables, so if the nullity of the coefficient matrix is greater than 0, then there will be infinitely many solutions. So let's outline the method we can use to actually produce or describe all of the solutions to a system that is consistent and in reduced row echelon form. So let's say our system Rx equals B is reduced and consistent. The first step will be to set the free variables equal to any scalars we like, and we'll use the variables C1, C2 up to Ck, where K is the number of free variables. Then what we can do, because we're in reduced row echelon form, is we can use each equation in the system to write the dependent variables in terms of the free variables. And then finally, as we'll see in our examples, this will allow us to express the full solution, x, as a specific vector, x sub p, plus a generic linear combination of other vectors that pop out of the process. So let's see this in action. Here we have a perfectly good reduced row echelon form system. In this system, it looks like we have two equations with 4 variables. And since we're in reduced row echelon form, we can easily locate our pivots. So we have a pivot in the first column and a pivot in the third column. Right away, we know that we're consistent because we don't have a pivot in the augmented column. And now we can quickly determine which variables are dependent and which variables are free. The dependent variables here are x1 and x3 because those are the variables that are represented in pivot columns. And the free variables are x2 and x4 because those are the variables that are in non-pivot columns. So what are the equations that we're communicating here? Well, the first row of this augmented matrix has a coefficient for x1 equal to 1, a coefficient for x2 equal to 3, a coefficient for x3 equal to 0, a coefficient for x4 equal to 6, and after the augmentation, we have a 7. So the first equation here is x1 plus 3x2 plus 6x4 equals 7. So we don't have x3 represented here because its coefficient is 0. The second equation is x3 minus 5x4 equals 1. So now we have our equations, we're in reduced row echelon form, and what we're finding is that we have free variables and we're consistent. So the Rouché-Capelli theorem tells us that we have infinitely many solutions, and our procedure from the previous slide says we should start by setting the free variables equal to our new variables. So we're going to replace x2 with c1, and we're going to replace x4 with c2. So let's do that in our equations here. x2 gets replaced with c1, and x4 gets replaced with c2. And now what we can do is we can solve each of the equations for the dependent variable. So I can solve the first equation for the first dependent variable x1, and what I should get is x1 equals 7 minus 3c1 minus 6c2. What about the second equation? The second equation allows me to solve for x3. This should give me 1 plus 5c2. So we've successfully written the dependent variables in terms of the free variables. So now we can write down the full solution. The full solution, x, will certainly have 4 coordinates, but we can't just arbitrarily fill this vector with 4 numbers because we might choose numbers that don't solve the system. Instead, what we can do is we can use the relations that we've developed throughout this process. So what is x1 equal to? Well, we just said that by solving for x1 in the first equation, x1 should be 7 minus 3c1 minus 6c2. So that's our expression for x1. What about x2? Well, x2 is our first free variable, and we decided that we were going to set x2 equal to any number we want, and we called that number c1. So x2 is equal to c1. What about x3? x3 is our second dependent variable, and we use the second equation in our system to solve for x3, and we obtain the expression x3 is 1 plus 5c2. Finally, x4. x4 was our second free variable, and we chose to set x4 equal to any number we want, and we called that number c2. So x4 is equal to c2. So now, here's the beauty of the process. The idea is that we can choose any numbers we want for the free variables, c1 and c2, but once those choices are made, in order to solve the system, our equations for x1 and x3 force the result to be a solution to the system. Now, we can take this one step further. I always like to separate this out into this solution vector out into its individual parts. One thing to notice about this solution vector is that each entry has three different types of terms. There are terms that are not attached to a free variable. There are terms attached to the first free variable, c1, and there are terms attached to the second free variable, c2. What we can do now is we can collect all those coefficients into individual vectors. So x sub p here will represent all of the coefficients in the solution vector that are not attached to c1 or c2. What are those coefficients? Well, in the first coordinate we have 7, and then we have terms attached to c1 and c2, so we should get a 7 as our first coordinate. In the second coordinate of the solution vector, the only term is c1, so we should get a 0 in the second coordinate for xp. Then in the third coordinate, we have a 1 that's not attached to a free variable. And in the last coordinate, we don't have any terms not attached to a free variable. So the particular solution here ends up being 7, 0, 1, 0. Then we can look at the coefficients for c1. Those coefficients are -3, 1, 0, 0. And finally, we can look at the coefficients in front of c2. Those are the coefficients -6, 0, 5, 1. And this now gives us a full expression for all solutions to the system. What this is saying is that if we want to generate a solution to the system, we can start with the solution 7, 0, 1, 0. That's one solution. But then we get infinitely many more solutions by taking any linear combinations we want of this vector x1 and this vector x3. So we're seeing the Rouché-Capelli theorem pan out here. This system is consistent because there's no pivot in the augmented column, but the nullity of the coefficient matrix is 2, which is the number of free variables. And if we have free variables, then we will have infinitely many solutions to the system. Let's look at another example. So this one's consistent at the other end of the spectrum. So here we have a reduced row echelon form system, but there are no free variables. So we have pivots in all three of the variable columns. So every variable in this system is dependent, and in fact the equations here are actually quite simple. The first equation is demanding that x1 equals -3, the second equation demands that y equals 2, and the third equation says that z equals 9. So there's only one solution to this system, so the solution vector is just xyz equals -3, 2, 9. Again, according to the Rouché-Capelli theorem, this makes sense. This system is consistent because there's no pivot in the augmented column. However, there are no free variables, so we have one solution, but we won't have any more. So we have exactly one solution here.